Hello everyone, today we're going to be discussing the fixed point section of the book. More specifically, we are going to be discussing the Arithmetic IP course for the adder, multiplier, and divider in sections 1.1 to 1.3. By the end of this video, you will have a solid understanding of how to implement any standard mathematical operation in hardware. This is an extremely useful topic since all control systems are just mathematical functions. What you're seeing now is a PID controller whose mathematical behavior was implemented using the very same IP cores that we will be discussing in this video. In addition to robotic control systems, there are many other important topics that require arithmetic circuits, such as artificial intelligence and signal processing techniques using mathematical operations like the fast Fourier transform. All of these highly valuable experiments will be discussed in this course. But in order to get to those levels, we need to go over the fundamentals of how to implement basic math in hardware. In this video, these fundamentals will all be covered. To begin, it's important to review how numbers are represented. In this video, when we refer to an SA.B or UA.B format, we are describing signed and unsigned fixed point numbers, where A is the total number of bits and B is the number of bits used for the fractional portion. So in school, you likely learned about the basic arithmetic circuits such as ripple carry adders, carry look-ahead adders, and array multipliers. While these circuits work mathematically, on their own, they are not sufficient for real hardware systems because they provide no control over when computation starts or when the result is safe to use. So, to make arithmetic circuits robust and timing aware, they are combined with simple sequential control logic to form a handshake-based module. As shown in the waveform, the inputs are updated first, a start pulse triggers the computation, and a done pulse is asserted later to indicate when the result is safe to use. This approach is the industrial standard because if an arithmetic module works in simulation but fails after deployment, the fix is always simple. It is simply to just modify the Verilog to make the done pulse happen later, giving the module more time to let the result settle. All IP cores presented in sections 1.1 to 1.3 follow this robust design standard and include additional pipelining techniques to guarantee that they work 100% of the time. In this video, I will focus on how to instantiate and integrate these IP cores into your own designs to implement any mathematical operation. So, the first two IP cores that we will discuss are for the adder and subtractor. Both of these IP cores can take any format of numbers, whether it's SA.B, UA.B, or SA, or U numbers. And both of these IP cores take in two parameters, and when these parameters are configured correctly, they will ensure that no precision or overflow errors occur, meaning that the result will always be correct. And so the first parameter is for the input width, and the second parameter is for the output width. Again, both the adder and subtractor take in these parameters and must be configured in this way to ensure that it's correct. So here is an example of how to use the IP core. So instantiate the adder and configure its parameters to process S16.8 inputs. Use the correct parameters when instantiating. So, to add two S16.8 numbers, we must configure the adder with these two parameters for it. So the input width needs to have its parameter be 16, since that's what our A was, the SA.B, so A was 16. So according to our rule, it needs to be set to 16. And the output width needs to be set to A plus 1, so that is 17. So, as a result, we configure our adder IP core with this instantiation here, and the output will be an S17.8 radix since the fractional bits remain unchanged. So now let's go over the Verilog multiplier IP core. So the Verilog multiplier, it can only multiply SA.B numbers, so all inputs must be converted into SA.B format before operation. And this multiplier has three parameters. It has a data width parameter, a fraction parameter, and output width parameter. And as long as you configure the multiplier's parameters when instantiating to follow this format, the multiplier will always produce a correct result that has no overflow or precision errors. So let's go over an example. So instantiate a multiplier and configure its parameters to process S16.8 inputs. Use the correct parameters when instantiating. Well, if we want to multiply two S16.8 numbers with this IP core, we must configure the multiplier with the following rules, which will result in this. So it's S16.8, A is 16, so our data width is 16. 8 was our B value, that was our fraction. So we configure the multiplier to have 8 for its B, for its fractional parameter. And the output width needs to have its parameter configured to 2 times A, and 2 times 16 is 32. So we use those parameters, and here on the left, this is what the IP core will look like when instantiated. And the output will be an S32.8 radix since the fractional bits remain unchanged. So that's how you would instantiate the multiplier IP core. And it's important to note that the reset is 0, and that will always be true. So the very last IP core that we need to discuss is the divider IP core. And the divider, it can only divide SA.B numbers, so all inputs must be converted into SA.B format before operation. And the divider IP core has 3 parameters, which are shown here. And again, to ensure that no precision or overflow errors come, we must configure them in this fashion. So, as an example, instantiate a divider and configure its parameters to process S14.7 inputs. Use the correct parameters when instantiating. Well, to divide two S14.7 numbers, we must configure the divider with the following parameters. We must set the data width equal to A. A is 14, so we set that parameter 14. The fraction is 7, so we set the fraction parameter to 7. And the output width is simply A plus B. Well, 14 plus 7 is 21. So from that, we use those parameters to have this be our instantiation of the IP core. So this is what that will look like. And again, the reset will always be 0, or in some special cases, if you want to manually reset it during operation, you can use that. But normally, that reset would be 0. And the output will be an S21.7 radix since the fractional bits remain unchanged. So this here is a complete design example of how to use these IP cores. So let's say we want to design a module called custom math block that can take in 3 numbers, x, y, and z, between this range and produce the following result. Well, to design that math block, we need to choose the format that we want to represent x, y, and z in. And S24.8 is a reasonable choice since it allows for 16 bits of integer and 8 bits of fraction, which can accommodate inputs of this range. And to implement this expression in hardware, we need to instantiate 3 of the IP cores. We need to instantiate a divider to handle this term. Then we need to instantiate an adder to add the result of this term to then get the total expression in the parentheses, which will be here. And then to get the overall result, we need to feed the output of the adder into the multiplier with the other input of the multiplier being y. And that will give us the result. So now let's go over the Verilog code used to implement this design in hardware. So this here is our Verilog module. At the top, at lines 3 through 8, we have our math block defined with its inputs and outputs. The inputs are configured with 23 bits since the format that we chose them to be in was an S24.8 format. Then from lines 11 through 26, we implement the divider. We configured the divider to accept S24.8 inputs by setting the parameters to 24, 8, and 32. We also need to define wires for the quotient of the divider and for the done pulse of the divider, which is done on lines 11 through 12. Next, from lines 30 to 44, we implement the adder. Since the quotient was an S32.8 radix, we need to change z from S24.8 radix into S32.8 radix before adding it to the quotient. On line 30, we create a wire called Z_CR, which converts Z into an S32.8 format. Then, using that converted wire, we can add it to the quotient. Also note that to make the adder compatible with S32.8 inputs, we set its parameters to 32 and 33. Also note that on lines 31 to 32, we define the wires for the sum and done pulse of the adder. Then lastly, on lines 48 through 62, we implement the multiplier. Since the adder's output was an S33.8 radix, the Y input needs to be converted into S33.8 format, which is done on line 48. Then, using that converted form, we can multiply it with the result of the adder to get the result. So, also note that to make the multiplier compatible with S33.8 inputs, the parameters are set to 33, 8, and 66. So this here is the simulation of our Verilog module with the radix correctly set for our module. So when x, y, z are these three values, our hardware calculates the result to be this. When x, y, z are these three values, our hardware calculates it to be this. And when x, y, z are these three values, our hardware calculates it to be this. So if you go and verify what all of these three cases should be, you will see that our hardware did indeed come to the right answer for all three cases. So you might be wondering, how did I set the radix of our simulation to be in the correct format? Well, if we go back to our source file, the radix of the input had 8 bits of fraction, and all three of our IP cores are made such that the bits of fraction never changes, and the IP cores are always in signed format. So based on that knowledge, we can set our radix like this, where we go to radix, real settings, then we use fixed point, and it's signed. All the IP cores interpret signed numbers because it's SA.B. So we click signed, and since 8 bits of fraction were used, we type in 8, and then we click apply. And just like that, we get our test cases in the correct radix.